Good day, everyone. We are Group 5 and we are here to present and explain our problem set.
Easy problem number 1. Compute for the frequency if the periodic time is 10 microseconds. First, list down the given. T is equals to 10 microseconds. Next, we will convert the microseconds into seconds using the multiplier for microseconds, which is 10 raised to negative 6. The formula for frequency is equals to 1 over T. The direct substitution for solution is F equals 1 over 10 times 10 raised to negative 6, which gives us an answer of F equals 100,000 Hertz or equal to 100 kilohertz.
Easy problem number 2. A simple electrical circuit is built using a 9-volt battery and 3 resistors connected in a series with resistance of 2 ohms, 3 ohms, and 5 ohms. How much current flows through the circuit and what is the voltage drop across each resistor using Ohm's law? So to solve the problem number 2, first add the resistance of the 3 series connected resistors, which is the 2 ohms, 3 ohms, and 5 ohms, giving a total resistance of 10 ohms. And using Ohm's law, I divided the 9-volt battery by the total resistance using resulting in a current of 0.9 amperes. Then calculate the voltage drop across each resistor. For 2 ohm resistor, 0.9 times 2 is equals to 1.8 volts. For 3 ohm resistor, 0.9 times 3 equals 2.7 volts, and for the 5 ohm resistor, 0.9 times 5 is equals to 4.5 volts. Adding all the voltage drops, 1.8 plus 2.7 plus 4.5 equals 9 volts, which matches the battery's voltage, confirming that the circuit follows the law of conservation of energy.
For problem number 3, calculate the power factor of an AC circuit with V equals 260 with a phase angle of 0 degree volts and I equals 6 sine 365T minus 23 ampere. The problem involves calculating the power factor for an AC circuit by determining the phase difference between the voltage and current. The voltage is given as a steady 260 volts with a phase angle of 0 degree, while the current is represented in the time domain as 6 sine 365T minus 23 degree ampere, which then can be translated to the phasor form of 6 with a phase angle of negative 23 degree ampere. This conversion allows us to directly compare the voltage and current phases, with the phase difference obtained by subtracting the current phase from the voltage phase yielding a 23-degree difference. The power factor, which evaluates how well the circuit converts input power into usable power, is the cosine of the phase angle difference. Hence, it is computed as cosine 23 degrees. This yields a power factor of roughly 0.9205, suggesting that approximately 92.05% of the electrical power is used effectively.
We now have here the problem number 4 for easy. An alternator has 4 poles. For letter A, at what speed must the machine be driven to develop 50 Hz? For letter B, what frequency is developed if the speed is 1800 RPM? To solve for letter A, finding speed when frequency is 50 Hz, we have the formula F is equals to P times all over 120, where F is the frequency in Hertz, P is the number of poles, and S is the speed in RPM. We will substitute the given values, which are P is equals to 4 poles and F is equals to 50 Hertz, which gives us the equation of 50 is equals to 4 times S all over 120. Now to solve for the speed, We would multiply both sides by 120 and divide both sides by 4, which results into 1500 RPM. Now to solve for the letter B, we would use the same formula and we will need to plug in the values of 4 for the P and 1800 for the letter S, which gives us 60 Hz.
Okay, so problem number one for hard. An AC power generator produces 50 amperes RMS or root mean square at 3600 volts. The voltage is stepped up to 100,000 volts by an ideal transformer and energy is transmitted through a long distance power line which has a resistance of 100 ohms. What percentage of power delivered by the generator is dissipated as heat in the long distance power line? So based on the given, the AC power generator initially produces a power of 180 kilowatts by supplying RMS current of 50 ampere at the RMS voltage of 3600 volts. So to minimize the power loss during the long distance transmissions, this voltage is stepped up to 100 volts using an ideal transformer which is stated in the given, and it is reduced by 1.8 ampere. Given that the long distance power line has a resistance of 100 ohms, the power dissipated as heat in this line, calculated using the formula of P loss, is equals to I to R, resulting in a loss of 324 watts. So in order for us to find the percentage of the generated power that is lost, we have to divide the power loss in the line by power delivered by the generator and multiplying it by 100, which yields at a percentage loss of 18%. So this will demonstrate the effectiveness of high voltage transmissions in reducing resistive power losses over long distances.
Next is problem number 2 for hard. We have a series RLC circuit, meaning a resistor R, an inductor L, and a capacitor C are connected one after the other to an AC voltage source. The key here is that current is the same through all three components. Mm. Next. Pi is the mathematical constant, approximately 3.14159. F is the frequency of the AC source given as 60 Hz. L is the inductance of the inductor given as 0.1 H. Calculation X L is equal to 2 times pi times 60 Hz times 0.1 H is equals to 37.7 ohms. Pi and F are the same in the inductive resistance calculation. C is the capacitance of the capacitor given as 100, which is equal to 100 times 10 raised to negative 6 F. And it is equals to 26.5 ohms. Next is R is the resistance given as 10 ohms. A is the imaginary unit, which is the square root of negative 1, used to represent the phase difference introduced by the reactances. XL minus XU represents the net reactance the circuit. If XL is greater than XC, the circuit is predominantly inductive. If XC is greater than XL, it is predominantly capacitive. This formula comes from the Pythagorean theorem applied to the impedance triangle in the complex plane, where the resistance is the real part of the net reactance is the imaginary part. And last, V is the RMS root mean square voltage of the AC source given of the 120 voltage. RMS voltage is the effective DC voltage that would produce the same heating effect. Z is the magnitude of the impedance we calculated in the previous step. Cos theta is the power factor of the circuit. It represents the fraction of the apparent power V times T that is actually dissipated as real power.
So next for problem number 3 for hard, a factory operates a piece of equipment powered by an alternating current supply of 300 angle 0 degree volts at 60 Hz. The equipment consists of an electric motor which can be modeled as a coil with an inductance of 65.5 millihenries and resistance of 22 ohms. Connected in parallel with a power factor correction capacitor rated at 52.3 microfarad. For optimal performance and power monitoring, determine A, the total equivalent impedance of the parallel network, B, the supply current drawn by the system, C, the overall circuit phase angle, D, the current flowing through the motor coil, and E, the current passing through the capacitor. So we have a given of 300 volts at an angle of 0 degrees voltage, a frequency of 60 hertz, a resistance of 22 ohms, and an inductance of 65.5 millihenries, and capacitance of 52.3 microfarads. To solve for the total impedance of the parallel network, we first need to calculate the reactance of the inductance, which is X sub L, and the capacitance X sub C based on the given values. So the inductive reactance is calculated using the formula X sub L equals 2 pi F times L. Substituting the given values, we get the 24.6929 ohms. And we calculate the capacitive reactance using the formula X sub C equals 1 over 2 pi F times C. Substituting the given values, we find 50.7186 ohms. To find the total impedance of the system, we store the value of X sub L as A and value of X sub C as B. Using these stored values, we get the impedance of 49.2204 ohms at an angle of 8.923 degrees. Next, we have the supply current. We calculate this using voltage over Z total. So the voltage is 300 volts of at an angle 0, and since we already calculated the total impedance in part A, we store that value under letter C. So dividing the two, that gave us a supply current of 6.0950 amperes at an angle of negative 8.0923 degrees. Next, we have the circuit phase angle, which is simply the angle of the total impedance, which we already have from part A. So the phase angle is 8.0923 degrees. It is positive, which means the circuit is inductive. In inductive circuits, current lags behind voltage. Next, we have current in the coil. Now we use the current divider rule to find the current flowing through the coil. So the formula is, so the current through the inductor is 9.0712 amperes at an angle of 48.3008 degrees. Next, we have, or lastly, we have current in the capacitor. We use the current divider rule again to find the current in the capacitor. After calculating, we got 5.9150 amperes at an angle of 90 degrees. So this concludes the solution to problem number 3.
Lastly is problem number 4 for Hard. So Jay is an aspiring engineer working on a side project with his friend Jay. They have built a small experimental AC circuit in their lab. The circuit is a simple series setup with just a pure resistor and a pure inductor. Jay measures the current flowing through the circuit and recorded it as I of t is equals to 5 pi over 6. So curious about the behavior of their circuit, they want to determine the following. A. What is the total impedance of the circuit? B. What is the value of the resistance in ohms? And C. What is the inductance of the inductor in henries? So to solve for this problem involving an RL resistor inductor series circuit, we analyze the given voltage and current equation using the principles of AC circuit analysis. So to find the impedance, we begin by converting the voltage and current expressions into phasor form. Then to solve for the phase linear, we have to use comparison of the equation using the formula Vn sine of omega t plus minus delta. So now convert the 5 pi over 6 and 2 pi over 2 into degrees. It will give us 150 degree and 120 degree respectively. So the impedance is now say is equals to 3 angle of 30 degrees. And to express this in rectangular form, we convert the polar form to rectangular. The impedance is now approximately 2.598 watt plus 1.5 I. From the result, the resistance is simply the real part of the impedance, which is 2.5981 ohms. Meanwhile, the imaginary part of the impedance represents the inductive reactance, which is 4.72 millihenry, obtained by dividing 1.5 by 3. And that concludes the explanation for solution number 4.
So that's all po. Thank you.